checking myself is when you're looking at the number that goes by bits. So when you remember when you by 2 bits, it's really sad. And that's part of the trick. Because I know when we first started, I wasn't doing that.
All right, so I can see that you guys are very excited about the exam on Thursday. So keep the enthusiasm up. Are there any questions from the practice exam session? Any questions about the practice exam? Yes. I'll leave it up to you to answer that question. Yep.
You mentioned this in class a little bit, but it wasn't quite explicitly stated. Exam 1 is going to cover the move instructions, the add instructions. Will it have any of the flags in it?
It will have the flags, but only up to the effect on the flags using the add instruction.
Okay.
Only
So
up to the add
no
instruction.
subtraction and no compare.
No subtraction, no compare. That's why when we talk about the compare question, I say it's out of the scope for this class for this exam. Okay. All right. Well, now that the homework, the flags homework is due, we can talk about the solution. So instead of just writing the code like that, what I'll do is I'm going to just create all the possible cases. So this way I'll use a spreadsheet to enumerate all the possible cases. So we have C, O, S, and Z flags. Those are the 4 flags. We can go from 0, 0, 0, 0, all the way to 1, 1, 1, 1. So what I'm going to do here is I will cheat a little bit here. So what I'll do is I'm going to use this column to go all the way up to 15, and then have these cells to be automatically filled based on these numbers. Okay. So this will be. Okay, let me see if there's an AND function here. Okay, equals and, yep. Cool. No, but that's not a bitwise AND. Is it a bitwise AND? No. Maybe it takes the operator. We'll try that. Ampersand 1. Nope, that's not. All right, we'll use the out cheat. I typically don't have to use the tool to do it, but since we are running a little short on time, I'll just go ahead and do it this way. Logical, it has logical AND, but does it have bitwise AND? Well, it's even, it's odd, that looks at the least significant bit. Doesn't seem to have bitwise AND. Oh well. That's okay. Sorry?
If you just use the word and, it should work. 1 space and. I'm just guessing.
Yeah.
No, never mind. That's what Google said. Google's usually wrong.
No, that's okay. I can just work this out myself. I mean, we can just do it manually. All right, no big deal. All right, the first case, everything are zeros. Is it possible?
Yes.
Okay. Give me an example where this will happen.
1 plus 1.
That will do it, right?
Yeah.
Because if you have 1 plus 0, the result is a 1, which means the Z flag is going to be cleared. The result is a 1, which is non-negative. The sign flag is a 0. Non-negative plus non-negative gets a non-negative. The sign makes sense. The overflow is a 0. And it does not generate any overflow because if you add the 2 numbers, if you look at it from the unsigned perspective, it does not exceed 255, then there's no carry. Is that making any sense? Okay. How about this one? This one's actually pretty easy too.
0 plus 0.
Please, yep, exactly. This is going to be 0, 0, 1, 0. I'm just using this number to give myself a hint, what is the bit pattern that I'm supposed to cover here. How about just the sign flag? That's an easy one.
-1 plus 0.
-1 plus 0?
Okay, doesn't matter.
It doesn't, well, it will take this one though.
Huh.
Anything that begins with a minus sign, I guess it will just take it and evaluate the expression itself. Okay, how about 3? 3 means we have 0, 0, 1, 1.
No.
That's an easy one. It's impossible. Why is it impossible? Can I prove by contradiction in this case? Let's just say that there is a calculation that ends up with both the z flag and the sign flag being 1s. But that's contradictory because the z flag being 1 says all the bits of the result must be 0s. The sign flag being a 1 means at least the most significant bit of the result has to be a 1. So those two are contradictory, and therefore this is not possible. Okay, not possible because z equals 1 means all bits are 0s. But sign equals 1 means the most significant bit equals to 1. Okay. Okay, let's take a look at 4 here, which is 0, 1, 0, 0. Okay. How about this one? Is it possible?
Yes.
Okay. How is that possible? Now this one is not possible, but the explanation is a little bit longer. It takes a little bit more work to explain this one. Okay. Tell me how the overflow flag can be a 1. The overflow flag is a 1, because if A and B are the two numbers that I'm adding, the most significant bit of the two numbers that I'm adding, and S is the sum of the two numbers, the most significant bit of the sum. So what is the equation of the overflow flag for addition? Okay, well, let's see. The first number is non-negative. The second number is non-negative, but somehow the sum is negative. That means the sign of the sum makes no sense, and the overflow flag is set. That's one case. What is the other case?
A and B and the opposite.
It's almost the same thing, except you flipped everything the other way. So the other case is A, which means the first number is negative, B, which means the second number is negative, and not S, which means the sum is not negative. Okay, so that's the equation. But why would this equation be useful to us? Well, let's break it up into two possible cases. Okay, the first case is not A and not B and S. Okay, I know we don't have to deal with this case, right? Why do I not have to worry about this case here? What is the bit pattern? What is the flag pattern that I'm trying to deal with here? Only with the overflow flag being a 1. This one says the sign flag has to be a 1 because S here is the sign flag of the sum. So I know we don't have to deal with this case. So we don't have to deal with the other case. Okay, needs not be considered because the pattern is XX, XOXX. Okay, so the other one is A and B and not S. Okay. If A and B are both set, what is it telling you? And you're adding the two numbers.
The most significant digit of both are 1.
The most significant digit of both the numbers are 1s, and so that guarantees one other flag has to be set as well. Which other flag has to be set? The carry flag. The carry flag has to be a 1, because remember what the carry flag is? The carry flag is the result of an OR based on the two numbers and also the sum of the two numbers and also the carry from the digit from before. So in this case, because those two numbers is going to generate a carry already, so the carry flag is already guaranteed. So in this case, this guarantees that the carry flag is also set. So that means it is not possible to have this particular case where the sign flag is a 0 and the carry flag is also a 0. Is that okay? Is that reasoning doing okay? Okay. But this case is not standalone, because every time you have these three being in these locations, all those patterns are not possible. In other words, the overflow flag has to go with either a carry flag or a sign flag. It cannot stand on its own. The only other time this will happen is the very next case, because the very next case is 0, 1, 0, 1. I don't really care about the Z flag here, because as long as it has this particular pattern here, I know it is not possible for exactly the same reason. Okay, so what I'll do here is to say C node A, and the same one here, C node A, and here's node A. Okay, any questions about this one? Moving on to the next one. So this one is 6, which is 0, 1, 1, 0. All right, is that possible?
Yes.
This one is easy. Okay, give me an example. The result has a sign flag, but it's not supposed to.
127 plus 2.
127 plus 1 would do it too.
Oh, okay.
Yep, plus 2 would definitely do it too. That's fine, okay. Are there any questions about this one? Because the result of 127 plus 2 is 129, but 129 has the most significant bit set. We're dealing with 8-bit numbers here. But the sign also makes no sense, because even though 127 plus 2 equals 129 seems to make sense, the bit pattern for 129 is also representing a negative value. So when you look at it from the signed perspective, the sign makes no sense. Yep.
There is no unsigned perspective, right? So the processor always interprets them as signed, and then the programmer interprets
Okay,
them as unsigned.
that's a good question. The answer to that question is the processor actually handles both signed and unsigned at the same time, because the carry flag is unsigned, but the O and the S flags are signed. But all these flags are being set by the add instruction at exactly the same time. So the processor actually makes preparation for both signed and unsigned interpretations later on. But when it carries out the add instruction, it's doing the same operation, and all 4 flags are getting set or cleared at the same time.
So it seems like it's up to the programmer how they want to interpret the number.
Correct. The programmer will choose which flags are relevant when they have to choose which conditional branch instruction to use.
Right.
So when you use JC and JB, JA, that means you are interpreting the numbers as unsigned. When you use JS, JO, JL, JG, that means you're interpreting the numbers as signed numbers. So your choice as a programmer is when you pick the conditional branch instructions. But the add instruction itself is blind to whether the number is signed or not, because the adding mechanism is the same whether it is signed or not. And that's mostly thanks to the 2's complement representation of negative values. Very good question. All right, moving on to the next one. How about this one? Well, I think this one we already know, okay? 0, 1, 1, 1. Because we already have seen this one, basically every time you see the sign and the Z flag being both 1 at the same time, it is not possible. So we'll go ahead and just, well, since it's just one line, we'll copy and paste it. So every time you see, a 1 and a 1 for the sign and the Z flag, we'll use exactly the same explanation. Oh, just by the way, when do you think this will happen again? When can I?
All 4 flags?
Yep. So 4 rows later, this will happen again. And then 4 rows later, nope, that's not what I want. It doesn't know how to paste, skipping a cell. All right, so we'll have to do it the hard way. Actually typing out. Is that making any sense so far? I don't really care what the other flags are. Maybe there's a different explanation, but impossible is impossible. If one pattern is good enough to explain why it is not possible, I don't really need the second explanation. So this is going to be a 1, 0 here, and this is going to be a 1, 1 here. Now you can see how I can fill up this table pretty quickly, because different combinations can share the same reason why it is not possible. It is the possible cases that are actually hard, because each one needs a unique way to make it happen. All right, so we are now down to 1, 0, 0, 0. Okay, only the carry flag, everything else are cleared. Is that possible?
Yeah.
Yeah.
Okay, how do you make that happen?
-1 and -2, I think does.
-1 and -2 will end up making the sign flag also set as a result.
It should be positive one shot.
What?
Shouldn't -1 and, oh, I'm sorry. No, I'm thinking of something else.
We just need a carry. So how about -1 plus 1?
Rest of the
Okay, we
zero
have
flag.
to 2 plus
-1.
-1.
There we go.
Okay. Up, wrong column. There we go. There we go. Is everybody convinced here? Now, there's no need to specify it like this because it is the same way. If you want to do this in a different way, it is the same as 2 plus 255. Because we're dealing with 8-bit numbers, -1 and 255 turn out to have exactly the same bitwise representation. Okay. If anyone prefers to look at things from the hexadecimal perspective, that would be the same thing too. Okay. 9 is 1, 0, 0, 1. Oops. Is that possible? This one is a little bit tricky. It is possible, and it is.
1 plus 255.
Yep.
Yeah.
Yep. Okay, next one is 1, 0, 1, 0. Is that possible? Both the sign flag and the carry flags are set, but the overflow flag is a 0. It is not possible, but how do you explain this is not possible? C, note B.
In order for the carry, the last bit should be 0. The most significant bit should be 0.
Okay. Well, let's take a look. Okay, we'll take a look in. Okay. We'll take a look maybe in sheet 2. Okay. So sheet 2 is officially our note B. Okay. So what we're talking about here is we want the sign flag to be a 1, and we want the carry flag to be a 1 as well. But all other flags have to be 0s. Okay. So we will take a look at the bit patterns. Particularly, we want to look at the most significant bits. Okay. So we'll take a look at the result. The result is the sign flag has to be a 1. So we're looking at 1, 1, 2, 3, 4, 5, 6, 7, 8. So this would be the result. We also want the carry itself to be a 1. Okay, that's what we want. So how can we make this happen?
2 negatives.
Hmm?
2
All
negatives
ones.
and all ones.
No.
Let's,
But we also want the overflow flag to be cleared or set.
0.
Clear.
Cleared? Oh, okay. If it's cleared, it's easy.
Yeah.
Yeah, we can actually make it happen. Sorry. I have to take back what I just said. I said it's not possible. Because I thought in my mind, the overflow flag is a 1. Okay, the overflow flag is a 0. It is possible. Never mind. So we'll just say this is -1 plus -1. How about this? This is my escape character. Ah, it shows up too. Double quote. No. Can't escape this one.
Or 255 plus 255 would give you the same thing.
Yeah.
Fighting it.
There you go. All right, next one, 1, 1, 0, 0. That should be possible. Because remember, the overflow flag has to go with one of the two. Okay, either the carry or the sign. So this one only has to go with the carry. The sign is a 0. So that means we're looking for something that looks like negative plus negative becomes non-negative. Okay, so how can you get a case where negative plus negative becomes a non-negative?
Just do the other example, but make them both negative. Number 6.
Plus -1 will do it.
128 plus -1 will do it.
-1.
So, yeah, plus -1. 128 plus -1 is going to do the trick. Well, the 128 is actually negative 128 if you look at it from the sign perspective.
Yeah, because there isn't a positive 128 in the bit pattern.
So in this case, this is actually 80 plus 0xFF. That would be the other way to look at it. If you just look at the bit pattern, that's what you're looking at. Okay. Any questions about this one? No. Okay. Next one is 1101.
Impossible.
It's not possible. Why is it not possible?
All and Z flags incompatible.
Okay. Is it possible or is it not possible?
I got it.
It's possible because we have this. Yep. That will make it happen.
Was that 128 and 128?
Hmm?
Yeah.
Decimal, right?
That's why I don't want to talk about 120 or negative 128, because the same bit pattern can be interpreted as 128 when interpreted unsigned. When you interpreted it signed, it is negative 128, but all I want to do is to specify the bit pattern, which is 1 followed by 7 zeros. Now, that's going to do it, because if you look at the calculation, I'm just going to do it on the whiteboard real quick here. So it doesn't even matter how many bits we're dealing with. So let's say we're dealing with only 4 bits, just to save time. These are pretty much, all zeros. 1 plus 1 is a 0 with a borrow, with a carry. Okay? So that means, C equals 1 because of that 1 here. The sign flag is a 0. What about the Z flag itself? The Z flag is a 1 because we have all zeros as a result. The overflow flag is going to be a 1 because we have negative plus negative getting a non-negative. So that's how we can generate this particular pattern. Last one. 1, 1, 1, 0. This one is also not possible. Okay? But how do you explain this one is not possible? I think our note B is supposed to answer this question. In other words, we are supposed to look at, oops. Okay, this time, I know it is not possible because the overflow flag is a 1. Now, the overflow flag being a 1 puts a lot of restriction on what kind of pattern we are looking at. Because if the overflow flag is a 1 and the sign, turns out to be a 1, that means, what we are looking for, if I look into sheet 2, we are looking for something that looks like this. Okay? 1, 2, 3, 4. We're looking at something like this because the overflow flag being a 1 means the sign makes no sense. But the sign being a 1 means we are adding 2 non-negative numbers. So now the question is it possible to generate a case like this where you have 0x, basically the first number has the most significant bit being 0, the second number has the most significant being 0, but somehow you end up with the most significant being a 1 and the carry flag also being a 1. The answer is not possible. The carry flag is not possible. The sign flag, yes, we can make that happen. But the carry flag is not possible. How can you prove that it's not possible? You just look at the largest value you can ever specify. So you can look at, this is the largest number you can specify. Yeah, it's being smart. Okay, but when you add these numbers together, what do you get? You get 1, 1, 1, 1, 1, 1, 1, 0 with no carry. So if you use the largest two numbers with the most significant bit being 0, and it still doesn't give you a carry, it is not possible. Okay. Yep.
Just to clarify, the sign flags, or the flags in general, they're not actually going to look at the numbers that you put in decimal. They're going to look at the bit pattern. So when they see it, they're going to look at the bit pattern as it starts with a 0. You're going to interpret it as positive then, not if you put 128 or something in there.
That is
In decimal form.
in decimal, right? Yeah. When you write the program in decimal, hexadecimal, or binary, it really is different ways of specifying the same bit pattern. So you can use whatever means you feel is more convenient to specify the bit pattern. But once to the assembler, it's nothing more than just a bit pattern specification. So it really doesn't care. I mean, if one of these bit patterns also specifies a character and a valid ASCII code, you can use a single quote and then the ASCII code. It works the same way. Yep. Yep.
So the flag, I just want to make sure, the sign flag is set only when the result switches its sign, or only when it becomes negative? Like,
Could you say that again?
if the sign flag sets when the result switches its sign, like from positive to negative and vice
No,
versa?
not switch. Whenever the result has the most significant being a 1, the sign flag is a 1. The sign flag is nothing more than a copy of the most significant bit of the result.
Only once the most significant bit is 1, only this way the sign flag is 1.
The sign flag is the most significant bit of the result. It's just, it's latched, which means it is remembered. So even if you don't store the result like in a compare instruction, the sign flag will still be changed, depending on the result of the operation. Okay. Now this one actually has a more formal proof. If you go back to the definition of half adder and how a full adder is derived from a half adder, you can actually use that equation to prove that it is not possible. Okay. Let's take a look at this one here. Do you guys still remember half adder and full adder?
Oh yeah.
Okay. Okay. So let's take a look at not even the other bits. Let's just look at the most significant bit and also the second most significant bit. This is the most significant bit. This is the second most significant bit. We'll just call this A, which can be a 1 or a 0. And we know this one is also a 0. This is a B. Okay. We want the result. Okay, let's take a look at the result of adding these two bits. Okay, 0 plus 0 is 0. Okay, A plus B can be either a 1 or a 0. Okay, depending on what A is and what B is. Okay, so we'll just say that this is kind of an unknown here. A plus B can also generate a carry. Correct? Because if A is a 1 and B is a 1, then 1 plus 1 is a 0, generating a carry. Fine. We'll put a 1 here. Then we have to add these two together. 0 plus 1 is 1. Do we have a borrow? So that means it's not possible to generate a borrow. I mean a carry in this case. Okay. Any questions about this one? This is our last one. We're done. So that means the solution should look like this. This one is also impossible. See sheet 2 in this case, because I use the entire sheet to explain it. Also note B. Okay, but this is really the best answer. The best explanation is this part here. You just look at the bit pattern. You look at how a half adder work, and you look at how a full adder work. It's impossible to generate a carry in this case.
So we'd assume there that A and B are both 1 because we want to try to get.
Because the
two
sign flag is a 1, but the overflow flag is also a 1.
Right.
So that means the two numbers that you start off with, they both have to be non-negative.
Right.
Yep. So you can see how the overflow flag is actually very useful because it helps us, limit. Okay, we only have to consider these cases here, and it just helps you eliminate a whole big bunch of test cases. Okay, so are we doing okay with the homework assignment? Kind of? Yep, go ahead. Okay. This particular homework assignment is really designed to help you understand the flags, because as you do the homework assignment, I'm hoping that you get a better understanding of how the flags really work, and how the add instruction is affecting all these different flags. So we'll save this file as a spreadsheet, and that's it. Cool. Now we have the first real homework assignment, because somebody was complaining, we don't have any real programming in this class. We're dealing with all the flags and all the Easter egg hunt, and excuse the reference to a certain religious, holiday. I'm not supposed to do that. So anyway, So here's your first programming assignment. It's a little bit messy, okay? When you look at the C code, it's pretty easy, but when you have to implement it in assembly, it's a little bit messy. So we'll talk about the messy part today. So that's why I talk about the homework assignment first, and then when we talk about the translation, especially with the logical operators, that's when things you have to kind of pay attention to that. So what we have here are four quote unquote variables. This is all in C code, so I can actually call these variables. Okay. If you don't know what this means, it is signed 32-bit number. Okay. It takes up 4 bytes, and you have to interpret it as a signed number. So we have a signed dividend, a signed divisor. I want to find the quotient and the remainder. One of these variables is actually not needed because I can reuse the dividend for my remainder, but we'll just do it this way, so it's really clear what we are doing. The first line is just making a copy of the dividend. The remainder starts off with the dividend. And the second portion here is a conditional statement. The conditional statement is nothing more than just making sure the divisor is not negative. Okay, if the divisor is negative, I flip the sign of the divisor. But if I flip the divisor, I also have to flip the dividend so that the quotient and the remainder still make sense. Is that working out so far? Yes? No? Okay. So after this conditional statement, I know that my divisor has to be non-negative. I will not give you test cases tricky, having a divisor being 0, because that will throw this loop into an infinite loop. There's no way you can get out of the loop in that case. Okay, so we'll start off quotient being 0. Okay, quotient is just really a counter in this case. It's counting how many times do I have to subtract until, okay, if everything is positive, this is basically just counting how many times do I have to subtract the divisor from the remainder until the remainder is less than the divisor. That's basically how kids do their division early, in the early stages before they know the trick of the actual multi-digit division. I can give you one example. So let's say 23 divided by 4. Okay, so what I will do, if I don't understand the real mechanism of doing division, I'm going to subtract 4 from 20. 23 is greater than or equal to 4. I subtract 1 from it. So now I have 19 as the remainder, but I have my quotient being 1. There's at least one 4 in 23. I look at 19. 19 has another 4. So now I subtract another 4 from 19. My quotient gets up to 2. So basically, this is your remainder, and this is your quotient. I will keep doing this. The next one is 11. This will go up to 3. The next one here, this is 7. This will go to 4. The next one is, this is 3. This will go to 5. But because 3 is already less than the divisor, I'm done. Okay? That's basically what this algorithm is doing. It's just doing division the long way. Are there any questions about the general logic of the division? Okay? It only looks complicated because I have to deal with the signs of the divisor can be different from the dividend. Okay, so I'm just doing that special case here, which makes it a slightly more challenging homework assignment. Otherwise, it's really easy. Okay, so the first case is if the remainder is negative. I know the divisor is positive already. So what I want to do is to flip the sign of the remainder before I compare that to the divisor. If after I flip the sign, it is greater than or equal to the divisor is definitely non-negative, then I have one more operation, at least one more operation to perform. Question?
Why? If I were writing this, I would determine what the result should be, the sign of the result, and then interpret everything as positive. Can we not do that? Then you wouldn't have to have all these error checking for whether or not it's positive or negative.
But the point of the exercise is to deal with all the conjunctions and all the disjunctions.
Okay. Okay.
Otherwise, you can just use diff L and be done with it.
Yeah.
One single instruction. So the point of the exercise is how to implement this using the logical operators. Okay. Now, I'll give you guys some tips, as to how do you start writing the program and how do you test the program too. The worst thing you can possibly do with a program like this is to write everything and then test it. Then you end up with like 60 lines of assembly code and you have no idea why the program is not working. Okay, so the second case is really just the flip side of this. Okay, in this case, I know the remainder is non-negative and it is greater than or equal to the divisor, so I have to perform another iteration. Inside the loop, I have a conditional statement. This is a single conditional statement. If the remainder is less than 0, which means it is a negative number, what I will do is I'm going to add divisor to remainder, because divisor is guaranteed to be non-negative at this point. So I'm just reducing the magnitude of the remainder in this case. It's still negative. It is possible it's still negative, but I'm reducing the magnitude of that. At the same time, I'm decrementing quotient because it's going in the opposite direction. Okay, this is going in the opposite direction. I have to decrement quotient. And in the other case, I will be subtracting the divisor from the remainder, and I'll be incrementing the quotient in that case. Okay. So the logic of the program, you can test it. I mean, you can just copy and paste this code into a C program, compile the C program and see it work. Okay, go through GDB and all the other stuff, so they can see how it works. Okay. The big question is not, the logic of this program. The big question is, how do I translate that into assembly language? That's your homework assignment. Okay. First thing first, how do we deal with these variables? Because I stated in the class there's no such thing as variables in assembly language programming. But what comes close to variables?
Registers or labels?
You don't want to use registers in this case because I think you'll run out of registers. Besides, I cannot test a program if you use registers. So you have to use memory operands for dividend, divisor, quotient, and remainder. So all of these must be memory operands. Okay. If these are memory operands, how do you allocate space so that you can have, these 4-byte signed integers? There are many ways to do it. Just give me one. The easiest one is .int, right? .int will do it. So each one can correspond to one .int declaration. And you probably want to use the labels too. In other words, you want to use dividend : and then .int whatever, because I'm going to change the values by the time I test the program. So are there any questions about how to handle the first 4 lines? How do you make quote unquote variables in your assembly program? No questions? Next question: where do I put these directives? In other words, when you do dividend : .int 0 or whatever, are we going to do it in the .text section, or are we going to do it in the .data section? .text. Well, the dividend is not changing. How about divisor?
Some of them will be changing.
Some of those will be changing. Okay, very good. You want to put everything in .data, because what I will do, I will explain that later on, when I explain the template of your program, because I will change these things before it gets to your part of the program, and then it will get back to another, it will go to another label, and then I will test whether your program actually does what it's supposed to do. So you have to put everything in .data. All the .ints, they have to go to the .data section. It's all going to be explained later. Do we know how to do this one? Assignment statement in C, and the right-hand side only involves one single variable. Sounds to me that the move instruction can be useful here, but not a single move instruction. You will need 2 move instructions, because the restriction is, all instructions can only have up to 1 memory operand. And both of these, the dividend and also the remainder, are going to be memory operands. So you will need 2 move instructions to get this done. What about this one here? Remember last time we talked about how to transform conditional statements? Okay, so we'll yeah, go ahead.
We're recording right now, right?
I certainly hope so. Yes, it is being recorded.
Okay, awesome.
Okay. So now, so I think we can handle this one, okay? From the discussion from last time, I think we can handle this one. Besides, this is a literal 0. That makes things a whole lot easier because you have one memory operand and one immediate operand here, and you don't need any extra instructions. A single compare instruction can do the comparison. Okay? Am I doing okay with this? Does everybody understand what is how to do this one here? Divisor equals the negation of divisor. I'm flipping the sign of divisor. Well, first of all, do we have enough pieces to do this? I'm asking you to build a little Lego thing. So the question is, do we have all the different blocks that we need in order to build something like this? It sounds like we don't, but we actually do. Just imagine there's one more 0 before the minus sign. Okay? That's one way to do it. There are other ways to do it as well. Okay? So is that okay? But does everybody get the clue? Okay? Just put a 0 in front of the minus symbol. So instead of being a negation operation, now it becomes just regular 0 minus divisor. And which instruction do you think will be useful here?
Subtract.
Subtract. All right, very good. So I think enough clue is given in this case. Quotient equals 0. A single move instruction can do it because once again we have an immediate operand here. It's a constant 0, and this is a memory operand. So that's not really too hard. We'll ignore this part first. Okay, the messy part we'll just ignore that for the time being, and we'll just look at the easy ones first. Okay, so that later on we can focus on the messy part. Okay, this is the easy part. Can we do something like that? Does everybody understand what is a plus equal operator in C? Okay. And as it turns out, if I had written this as remainder equals remainder plus divisor, it's actually harder to interpret. This is really easy because your add instruction is inherently a plus equal operator. The second operand is also the destination. So that makes sense. You just have to flip the direction and you're almost done. It's just that you have to take care of the problem that you can only have up to one memory operand for all of your instructions. But that's an easy one to get over because you just have to move one of these into a register and then use the register in the second instruction. Okay? What about quotient minus minus? In this case, I could have written it as minus minus quotient. It doesn't really matter whether it's pre-increment or post-increment. Do we know how to decrement by 1?
Yeah.
Which is the same as minus equal 1. Okay, that should be pretty easy. Okay, and the same thing over here. Basically we're just flipping, add to subtract and subtract to add. So I think we are okay with most of the pieces here. The only piece that is kind of difficult to deal with is how do we deal with this big old mess of conjunctions and disjunctions and whatnot. Okay, that's the focus of today's lecture. Okay, this is our focus today. So let's go to the notes related to this part, and then we'll go from there. Okay, so go to 10. Control structures 1, which is the new notes. I think it's better than the other one. And you're welcome to read either one. Okay. So basically we are done with conditional statements, pre-checking loops, and post-checking loops. Are we doing okay here? Does everybody still recall what we talked about last time? I'll just kind of quickly go over these. With control structures like a conditional statement, what you do is you start with the general structured conditional statement. And then the first thing you do is not even to translate it into assembly, but continue to use C code, but you translate it into C code that is not structured anymore. Because assembly code is not structured. There's no open curly brace and closed curly brace. There's no such concept as a block. So this is the first step. And if you look at this pattern here, this is really just a template. The template has 3 chunks. The first chunk is the condition itself, the second chunk is the then block, and the third chunk is the else block here. The translation is turn the condition and put a negation sign in front of it. Instead of having a block right after that, you have a goto, because this will translate this into a conditional branch instruction in the end. Block 1 is still here. This is the same as block 1, but after block 1, you will need an explicit goto to go to the end of the conditional statement. L1 represents the entry point of the else part, so that when the condition is false, you would go to that particular portion. Block 2 is our else block, which is the same block as here. And then L2 is the end of the entire conditional statement. In other words, this is mechanical. Once you understand what the transformation is about, it's completely mechanical. If you have no else, then it's basically just looking like this. Or if you prefer, you can say if there's no else, then the else block is just empty. It will do the same thing, it's just you have some additional branch instructions that are unnecessary, but it is still correct if you just consider block 2 as an empty block. Are there any questions so far with the conditional statement, the transformation as a first step? No questions? What if block 1 is another conditional statement? Then you do the translation recursively. The only thing you have to be careful about when you do this recursively is you can only have one label L1 and one label L2. So when you choose the label name, you have to choose carefully so that the label name itself is also reflecting the structure of your program. Okay? Any questions about this portion? No questions? Yep, go ahead.
This C, what variable type is C?
C is a condition.
Okay.
It can be something like this short, it can be something like this long. I don't care what it is. I just take the negation of whatever it is when I do the transformation. Okay. Next, pre-checking loop is even easier. The pre-checking loop looks like this. While condition C do block 1. So what we do when we translate that is to put a L1 before everything else, because you have to go back to the entry point to test the condition again. If the condition is false, you go to L2, which is our exit here. L2 is basically an exit label. When we go to L2, we are basically saying we're done with the loop. If you're not exiting, that means you have to perform the body of the loop, which is block 1. At the end of block 1, you need an explicit go to go back to L1 so that you can perform the next iteration. You have to check whether the next iteration has to be performed or not. Are we doing okay with 3.2? Okay. Next one is a post-checking loop. We are not even using a post-checking loop in the homework assignment, but it's really even simpler. Okay, this one is even simpler because a do-while loop is saying perform block 1 first, and then check condition C. If condition C is true, go back and do block 1 again. That's what it means when you have it in C. So when you deconstruct it, you're using only go-tos and conditional branches, then it becomes L1, because we know that we potentially have to come back to this point, and block 1 is still block 1 over here, and the end looks like this. If condition C is true, then you go back to L1. Does it make sense? So we are done with the control structures. What is kind of messy is how do we deal with negation and also deal with and deal with or. Okay, that's the only part that we have not talked about. Let's deal with negation first. If you have something that looks like this, then you can translate that into something that looks like this. This is all in C. This has nothing in assembly in it. Does it make sense? If not condition C, go to L1 is what I want to express. Does it do exactly the same thing if I transform that into saying if C, go to L2, and L2 is, in this case, a continuation label? But if C is not true, I'm not going to go to L1. I continue execution with the next statement. The next statement says go to L1. Do these two do the same thing? They do the same thing. In fact, you can see the second one is longer. So why do we want to make something that was shorter into something that's longer? What did we achieve in this case? the negation is gone. Because at this point, we are sacrificing instructions to make the expression simpler and simpler and simpler. That's what we are doing. We are reducing the operators by consuming instructions. Okay, go-tos, conditional branches, those are all instructions. Are we doing okay so far with how to get rid of a negation? Well, no questions? Then we will talk about how to get rid of a disjunction. If the original code has a disjunction and it says if C or D go to L1, well, this is a pretty easy one, because what this means in C is if condition C is true, we don't even bother to evaluate condition D, just go straight to L1. That's the first statement here. If condition C is false, then we'll give D a chance and say, okay, let's evaluate D. If D is true, we'll also go to L1, and that's what the second conditional statement is about. In other words, you will only continue execution with whatever is after these two conditional statements if C and D are both false. Right? Is that behavior the same as what this statement is supposed to do? Okay, so that's basically just an easy translation. Conjunction. The original statement says if C and D are both true, that's the only case, if and only if C and D are both true, go to L1. That's what we want to accomplish. What we want to do is to say, if condition C is false, we'll just go to L2 and continue execution right away, because in a conjunction, if one condition is false, then you use the short-circuited evaluation and you just skip the second part and continue execution. Does that make sense? What if C is true? Well, if C is true, that means we're continuing with the second statement, because we have to check D. This is a conjunction. If one condition is true, it doesn't guarantee the entire conjunction is true as well. So only at this point we have to evaluate D, and if D is true, then we go to L1, which is the original purpose, the purpose of the original code. Yep.
So if we used C on the second line instead of D, it would not guarantee both conditions are true?
If you use
C on second line.
why would you want to use C on the second line? Then you're double checking the same condition. What about D? You have to check D at some point.
You would have skipped, if you had C on your second line, you would have skipped that whole line anyways.
But can we switch C and D on line 1 and 2?
Okay, the question. Okay, the question is, can we switch this C with this D? Right? Is that the question? The answer is no, because the C programming language specifies when you have a logical operation like this, the first condition is always evaluated first. Okay, and that's why you can write shortcuts when you have a loop. You can say, while I is less than the size of the array, and blah blah blah, and so on and so forth, because the first one becomes a guard condition for the rest. If your index, in a situation where you are doing array indexing, if your index is out of range already, it would fail condition C in that case, and it won't even bother to evaluate condition D, which makes use of indexing operation to look into the array. So the order is actually important in this case. You cannot flip the order. Okay, is that okay? Are there any questions up to this point? Because we have just covered all the logical operators. Yep.
Where should we put that label L1?
Label L1?
Should it go
Label L1 is just somewhere. I mean, this is really just saying, if you see something like this, transform that into something like this. We don't care how label L1 is actually defined. Label L1 in this case is probably the result of a conditional statement, a while loop, or do while loop. We don't really even care, who is defining L1. If the original code, if you have a line that looks like this, we transform that into this. Okay? Is this mechanical enough? You see this, you do that. You see this, you do that. You see this, you do that. Okay?
I like that. That's good.
Well, this is how compilers work. I mean, compilers actually just do something like this, really, really quickly. All right. Now, this part talks about simple reductions. In other words, sometimes maybe we don't have to use that particular mechanism and generate all these conditional branches and additional labels and whatnot. So that means when you see a negation like this, okay, inside a conditional branch instruction, there's no need to go through all that trouble to make new branch instructions and new labels and whatnot, because all you have to do is to change the way you compare, and then it expresses the opposite of what you originally wanted to do. Okay, it is not the case that x is greater than or equal to y. Isn't that just saying x is less than y? So that means whenever you can do something like this, just do it this way. Okay, there's no need to use the mechanisms that we have just talked about. Even though it is not wrong to do it that way, it just saves you a lot of time if you do it this way. The second example is if you have something that looks like this, x is less than y or x is greater than y, well, all that means is x is different from y. So you just turn it into a not equal comparison instead of actually going through all the trouble to take care of the disjunction. In other words, use common sense. Okay, if you can combine operators and make it convenient and not have to go through all the mechanical steps, just avoid the mechanical steps.
But this is only a human step. The compiler doesn't do it.
The compiler can do this too. The compiler can look for patterns that looks like this and perform the same type of transformation. Yeah. In fact, there's a special compiler optimization technique called a peephole optimizer, and all it does is to look at localize and just look at particular patterns and say, oh, I see this pattern here, it is equivalent to this pattern, but the second pattern is quicker or more efficient to implement, and it will just perform the transformation.
What's that called?
Peephole optimization, like a peephole.
Okay.
It means localized optimization. It doesn't take take global effects into consideration.
Cool.
There are other techniques in compiler optimization that takes the look of your entire subroutine in order to do the optimization. And this kind of technique doesn't do that. It's really just a localized transformation.
Okay.
Okay, any other questions? All right. Well, we have all the pieces that we need already. We really do. So we'll go through an example about nesting and labels. Okay. Now, in the previous section, we used labels like L0, L1, and L2. But because you have to perform these transformations many, many times, you probably have to come up with a way to label or name your labels so that they don't have collisions. The worst thing you can do is to use the same label twice, but not the definition, but the reference to the wrong label. Because the wrong label is still there, the assembler cannot complain, but your program will be branching to the wrong point. Okay, so that means these things can come in handy. Indentations. Okay, you already understand the importance of indentation in high-level programming. You can do the same thing in assembly. There's nothing wrong with using indentation in assembly language programming. The label definitions can be indented. In other words, you can start with tabs or spaces, and then like 10 spaces over, and then you start L1:. There's nothing wrong with it. The assembler will accept that without any problems. Okay.
So that's the label tab L1. That's different, just L1.
No, he's saying hit on the keyboard.
You can basically have empty spaces before the definition of a label.
Okay.
A label definition does not have to start with column 1. Okay. Use indentation. Use more useful names. Instead of using L1, L2, and so on, you might want to start to use loop begin, loop end, or begin loop, end loop, that sort of thing. If you have 2 loops, you can label these as loop 1 begin, loop 2 begin, and so on. Just make sure that you have some sort of naming convention that when you look at your own labels and references, you know which one you're talking about. Also use labels like else if, and if, and so on. Okay. Those will come in handy as well. Sequential numbers. Okay. So in this particular case, the first one would use the sequential number of 1, and the second one you would use a sequential number of 2. Okay, if things are in the same indentation level or the same nesting level, you just use the next available sequential number. Okay. Any questions up to this point? Any questions? Nested constructs. How do we deal with nested constructs? Well, you can use the suffix method. In other words, when you deal with the conditional statement that is inside a loop here, you basically label the conditional statement as loop 1 if 1. So the label for this and if, you put a loop 1 as a prefix to that label. So this way, your label names cannot have collision because they are all properly prefixed. If you don't know what I mean by this, you can just come up with your own way to come up with the label names so that you don't get confused when you look at your program. Any questions up to this point? No questions? Okay. Okay, there are only two things to remember. One is to use sequential numbers. When you have constructs at exactly the same indentation or the same nesting level inside the same local scope, use sequential numbers. When you have structured code, in other words, nested code, use the outer construct as a prefix for the inner construct's label. So this way, if you follow these two rules, then there will be no chance of using the same label again. Okay. Boolean operator reduction transformation. All right, so let's take a look at this one here. We talked about this already. And Boolean operators these are low-level transformations. So we do this as the last things to do. We have talked about this already, haven't we? It's just that last time this looks like this is the C that we were all talking about. This is the D that we were talking about. This is L1 that we are talking about. Okay. Now the only difference here is I don't have L2. This used to be L2, but instead of using L2 as the label, I just add a suffix of _1 to represent this is the end of that conditional statement. Okay. You can also use end if if you want to. Oh, I cannot use end if because it's already going to end if 2. So this is I just have to use an _1 in this case because just adding more suffix, it will make the labels unique. Are there any questions? No questions?
You can't use end if.
Well, this is not an end if actually, because this is already a quote-unquote flat conditional statement. It doesn't have structure to it, so there's really no end if, so to speak. Yep. But you can use end if you want to. Just change this one to quote-unquote end if. Yep. Go ahead.
It seems to me like the simplest way would be to refer to exactly where they go to the line to go to, supposed to jump to. Like if it's going to jump up to line 108 of your code.
That's not going to work because your program, because you will be inserting code all over the place. You cannot write programs like this sequentially. This has to be done in a structured way, which means the line numbers will shift. So using the line numbers may not be the best approach.
Because you'd have to change it up like a million times. You'd have to change it a million times.
Yeah, but if you forget to change one of them and you end up to have an actual label there, then you'll be going to the wrong label, and those bugs are really hard to fix. All right. And number 7 is a longer example. Okay, and you can tell from the thumbnail here that this is a longer example because it goes like this. And it goes all the way to here, and we are done. All right. Okay, now you guys can start on your homework assignment. Okay, let's roll back here and then start from the beginning. Okay. So what we have here is to start off with. Well, we started with a perfectly structured C program. Okay, I can't even remember what the C program actually does, but that's not even important because the whole point is how do we translate this into assembly. Okay, it looks kind of messy. I mean, it has a conjunction in the inside, and then it has a disjunction on the outside. Not unlike your homework assignment. Okay, it has a conditional statement inside the while loop, inside the while loop. Okay, it has 3 nested levels. But if we do it step by step, we can do it. So the first thing you want to do is to just copy and paste the program, but insert the pound sign to comment out everything so that your assembler would not complain about the quote-unquote C code here. Okay. Depending on your mastery of VI, you can do it with one single command, or you can just go ahead and just go to each line and insert the pound sign at the beginning. It's not a big deal. Okay. Yep.
What's the command?
It's muscle memory, so it's really hard for me to say. I have to actually do it on the keyboard. It's colon 1 comma $S/ caret / pound space /G enter. Okay.
Oh yeah.
Well, it's all recorded, so you can actually play in slow mo and hear me say it again. Then it will sound like really in a deeper voice, right? Slower,
An hour and 5 minutes.
deeper. Yeah.
You should just talk like that one whole period and make it break. Like that doesn't come in class that day. Man, the audio's off.
Audio's off. Silent movie. All right. Okay, but that's not a big deal because your program only has so many lines. Okay, if you cannot figure out the one command in VI to do it, it's not a big deal. Okay, just go to each line, put a pound sign, and forget about trying to get it done in VI. Don't let VI become your obsession. Okay, that's not healthy.
Sound like from personal experience.
Okay.
It's not healthy.
Well, I have some other obsessions here, just not VI anymore. All right. So the first part is how do we translate X, Y, Z, which are variables. They can change when we execute the program into .int structure, .int directives. It's pretty easy. We just say X is the label of the first byte of this .int here. Y is the label of the address of the first byte of the .int here. I have to say it that way because I really cannot say that X, Y, and Z are variables because we are now programming in assembly. Okay. But for the most part, it's fairly easy. The important part is they have to be in the .data section because otherwise you will not be able to change the values of the variables. Okay. The rest of the program, start with the usual stuff. You switch back to .text to start your program. .global _ start, so the linker knows where the entry point is, and then you specify the entry point. We don't have to deal with main as a subroutine at this point, so don't worry about how do we do subroutines, how do we return. Don't worry about that. Everything is going to be talked. We'll talk about that later. So now you also have to insert the exit code. That part is already done. If you look at the homework assignment, where is it? Right here. If you look at the homework assignment, I give you a template already, which resembles what you just saw in the class notes. Okay, the class notes here, the longer example, there's no need to actually even do the video recording because this is actually in the notes. I mean, if you click that link, it will bring you here. Initialization is pretty easy. Okay, in other words, we are dealing with this line here. That's it. We just need to use. Oh, by the way, what kind of operand is this? We know it's a memory operand, but there are many memory operands in the x86 architecture. What is the name of this particular one? It's a direct operand. Okay, it's a direct operand. Do not put a $ in front of the x because that will turn it into an immediate operand, and it makes no sense as a second operand. Okay, and the other one is pretty much the same thing. We know how to do that, and I also take care of this one too. Okay, because they're all just initializations. So now I took care of all the initializations. But you can see how I interleave my assembly code with the C code. Okay, and that's really important. You can also see how my assembly code has the same indentation as the C code. That is also important because now just by looking at the shape of the indentation, you have an idea of, okay, but what is this line doing, and which part of the C program is it trying to implement? It becomes crystal clear right away. Okay. Any questions about this transformation process up to this point? Okay. The easy ones, I don't think you really have to test it individually. So for the most part, for something like this simple, you can test it if you want to. Just run GDB, put a breakpoint on that line, make sure it does what it's supposed to, and then you get the confirmation, and then move on. The other thing that will be useful at this point is to use some kind of revision control mechanism. Revision control means there's a mechanism where you can quote unquote save different versions of your program, so that later on, if you make a mistake and the program doesn't work anymore, you can compare the latest changes that broke the program with the version of the program that still worked up to a certain point. Okay, and the result of the difference can be visual. It can display the differences visually, so that it allows you to look at the differences between two versions really quickly. Okay. Does anyone want me to do a quick demonstration of how to look at the diff? Okay. So what I can do is to look at just these two versions. Okay. So I'm going to copy and paste this into one text file. Okay. So we'll go ahead and start up a new terminal here. Go to today's 0228. We'll just call this v1.s. Okay. Copy and paste, and then we'll do the other one as v2.c, v2.s, and it'll be this one here. After I added some more instructions, so the middle button pastes Control D to end. So now we have two files, version 1 and version 2. If you don't want to deal with RCS or Git or one of those tools that are actually designed to do revision control, the simplest way to do revision control is once your program is working up to a certain level, save it as a different name. Just copy that file to a different name. If you don't know what name to call it, you can just use a sequential number, or you can use the date and also plus the time as a code, so that this is a unique version, this is a unique version. Okay, so the question now is how do I compare these two? There are many tools that will allow you to do it, but Vim can do it. VI can actually do it. VimDiff is a tool based on Vim. It allows you to compare the differences between two source code, two text files. Any text file is fine. And it displays it like this, really nice. On the right-hand side, you can actually, on the left-hand side, you can see this is v1.s, the first version, and v2.s is on the right-hand side. When you see a horizontal bar, it means that line was missing before. In other words, it was inserted in the new version. Is that okay?
So it automatically spaces it by putting in the horizontal line to demonstrate that?
Yes. That makes it very nice because now it is clear what lines you added in the new version. If you make changes to one line, in other words, you're not inserting, you're changing one line, it will highlight that as well. It basically saying this line was there already, but the new version is different. If you delete lines from the program, in other words, if the new version is missing certain lines, it would just be the reverse of this. The new version would have a horizontal bar where the old version has the actual code. Yep.
I don't think I really understood what you said. Could you show that or something?
Blah 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 blah.
I kind of understood what you said, but could you?
Okay. This is a nice little tool that will allow you to compare two text files. There's actually a VimDiff 3 that allows you to compare 3 files at once, but I think 2 files will be fine for this project. And what it does, okay, let me just go all the way back out. Okay.
Well, no, I understood all that stuff except the last part you're saying, the switch in or whatever. Okay,
well, the best way to do it is to do it using an example. So what I would do is I would go to the new program here, and let's say I accidentally took out the last instruction, which means the program is going to crash. So, and I'll go ahead and make some changes here. I will just say, this is easy to implement. So this line has changed. I did not insert a new line here. I did not delete the line. I just simply changed the line. Okay. So now we have all the different types of changes that are possible: removing a line, adding a line, changing a line. So if I use vimdiff again, you can see if a line is changed, it is highlighted. I know it's really hard to read on your screen, but it is basically highlighted using this kind of fuchsia and purple color, which means the line has changed. It doesn't know this is just a line of comment, so it will still highlight it as being changed. The vertical bar means, okay, let me just change it here. The vertical bar between this line and this line here means this line was not there before, and now we have a new line here. And then at the end here, this line was in the old version, in version 1, but I accidentally deleted in the new version, so that's why it is replaced by a horizontal bar to mean that this line is deleted in the new version. Is that okay? Just play with it. You will get used to the notation pretty quickly. It's really a nice tool that allows you to compare any type of text files. Are there any questions about vimdiff? Nope. Okay. All right. So here we have adding. Okay, so the adding part is pretty easy. I'm just focusing on this instruction here and implement it, because we cannot say add xz. So that means we have to move x into a register first, and then add the register to z. Okay. I think after you read this portion here, you would have done like 90% of your homework assignment, if not more. And then what we do is take care of the innermost conditional statement. Now this is getting into how do we get started with the program? I personally always start with the innermost portion of a nested structure. Okay, now what you want to do is up to you. Okay, because you can actually start with the outermost constructor and test the program that way as well. But I would usually start with the innermost and test that portion before I move my implementation out one level. So now the question is, how do I implement my conditional statement? My conditional statement used to have something that looks like this. But in order to translate that into a flat structure, I would have to use this instead and have to go to end if one, and end if one is here. Does everybody see what I just did here? It's a transformation for a conditional statement, turning structured code into unstructured code using gotos and labels. Are we doing okay so far? Okay. This was there already, so this is not new code. In other words, the transformation was I had something that looks like this. I transformed that into something that looks like this, plus the label at the end. That's the only transformation. If you want to find out, how one version is different from the other version, just do what I just did. Okay, copy and paste it into an actual text file. Use vimdiff to look at the differences. That will give you a pretty good idea of the differences between the versions. Okay, Demorgans-Law allows us to simplify the negated disjunction a little bit. Excuse me. This is the Demorgans-Law. Basically, when you have the negation of a disjunction, it is the same as the negation of each component, but you turn the, I think I missed one negation on the, no, this is right. The negation of a disjunction is the negation of each component, but then you join everything by conjunction. Can you guys all read this part here and understand what it means? Well, does it make sense though? Can you double check and make sure that that makes sense? How can we do that? You just use a truth table. Okay, use a truth table to double check the 4 possible combinations: x being true, x being false, the y being true, and y being false. There are 4 possible combinations. So the transformation is like this. Now you can also see how I do my transformation. Every time I take one version and transform that, I use the C, comment symbol to say that this is no longer what I'm dealing with. Instead, this is what I'm dealing with. In other words, even without revision control, I use commenting to keep track of the transformations. Does everybody see what I'm doing here? I'm transforming this into this. Is that okay? All right. So now we still have a big old mess here. We have negation and conjunctions and stuff like that. So now we're going to take care of the conjunction. So the conjunction, okay, in this case we have, okay, we lost the disjunction when we transformed, when we used Demorgans-Law. That's how we got rid of or how we changed the disjunction into conjunction. So now we have a conjunction, and you have to observe the nested level of the parentheses. This is one chunk, and this is another chunk. This is the operator, okay? So we apply that transformation that we talked about earlier for conjunction, so that this is now turned into this statement, followed by this statement. Is that okay? No questions? And then in the next one, we take care of the simple transformation. Okay, the simple transformations you can actually use. You can see how I use commenting here to take care of the simple transformations. The easy one is this one here. Okay, if I scroll back to the previous version, it already has this, but it has no assembly version. There's no implementation in assembly. This is all comments. So I look at this and go like, oh, if y does not equal to 0, go to and if 1. I can do that in assembly in only 2 instructions, right? The first one is going to be a compare instruction, and then the second one is a conditional branch using the Z flag. Is that making any sense so far? This goes all the way back to the pattern of transformation, going from C code into actual assembly code. Remember last time we talked about, okay, let me use a text editor here. We're going to go over time a little bit here because I think this is important. Remember last time we talked about something that looks like this. If x, r, y go to label L1, and how to transform that? Maybe? No? Okay. So the transformation is to use a compare instruction. Now the compare instruction definitely, you have to specify B or W or L here. It can be implied, the width of the operation can be implied depending on the operands, but I would not rely on the implied width. I always specify the actual width here. So you have to remember to specify the actual width. But you have to reverse the order of the operands. In other words, if x goes first, then it becomes the second operand, and if y is on the right-hand side, y becomes the first operand. Okay, that part is actually important for this trick to work. The second instruction is going to be a conditional branch instruction based on the relationship to L1. Okay, briefly, do you still remember this part from our last discussion? So the way you read this is, in C code is pretty easy. If x relates to y using R, go to L1. But when you read it in assembly, it's the same way, except you have to skip places a little bit. Basically, it becomes jump if and only if x relates to y this way to L1. Okay, it's a little bit awkward because the order of x and y are flipped. But that's basically just a template. If you do it enough times, it will sink in, and you just know how to deal with this. So in our case, what we have here in our code is y does not equal to 1. So basically, it becomes y does not equal to 1. Oops, go to some label. It's not L1 and if 1 and if 1. So if I apply the same thing here, the first thing I have to decide is really whether I should be using byte compare, word compare, or long word compare. Okay, in this case, let's say it's long compare. Then I do the same thing. The second, the right hand side becomes the first operand, and that's a constant of 1, and that's why I use an immediate operand. Y in this case is a memory operand, it's a variable, it's a memory operand, but since I'm only using up to 1 memory operand, that works just fine. And then the second instruction is a branch, conditional branch instruction. The R is the same as the relationship in the original expression. This relationship is not equal to, so you just say not equal to. NZ means not equal to, because remember, compare is the same as a subtraction. If after a subtraction you don't get 0 back, what does that tell you about the two operands? They're different. Okay, so that's why it's a JNZ. If you prefer, it is also known as JNE. E means equal. They are synonymous. Basically, they map to the same instruction. Okay, and then you just use exactly the same label 1 here. Does everybody see how this is a mechanical process? Going from the C code that looks like this to the assembly code that looks like this. Every time you have a simple comparison, whether it's larger than, less than or equal to, or whatnot, you can just do it like this. That's the end of the transformation. These are the things that we can actually transform directly into assembly code. So that's basically what I'm doing here. I'm transforming y does not equal to 0 to, oh, where is it? Down here. Okay, so I'm transforming that into a compare immediate 1 to y, branch if not equal to 0 to end if 1, which is down here. Okay, so I'm just really taking care of the program step by step until I break it all the way down to simple comparisons. Then I can replace that with a compare and a conditional branch instruction. Yep.
Question: if x and y are the same, does it jump that J and Z line and go straight to?
If x and y are the same.
Like if it is 0, if the Z flag is set, does it go straight to the next line, or how does it do access?
We are not done with. We haven't implemented this one yet. Okay, so if you want to take care of this one, you will have to translate the other conjunction. Okay, so that it gets translated into this, and then in the next step, we actually do the translation. In other words, we translate this into the assembly code that looks like this.
He was asking if the condition's false, does it just ignore the jump and continue down?
That is correct. If the condition is false, you continue. Yep. But you can see this one this time, because x is a memory operand and y is a memory operand, I have to go through a register EAX in order to finish the comparison, because compare cannot take 2 direct operands. It can only take up to 1 memory operand. So are there any questions about the transformation process? It's tedious, okay, but you can do it step by step. How do we test the program?
Compile and run.
Well, what you need to do is to look at the original logic. Okay, look at the original logic and figure out when it is supposed to actually perform this statement here. Okay, come up with some test cases, set up your .ins to reflect the test case, and then set a breakpoint at the right places to see whether your program is going there at the right time and skip it at the right time as well. Okay, so you have to do all the testing before you move from this innermost nesting level to the next nesting level, because the worst thing that can happen is, the code is not fully debugged yet, and then you add additional code to it. Then when the program doesn't work, then there's no telling, was it the old code that was having problems, or was it the new code that was having that is having problems. So you have to do it step by step. Revision control can be very, very helpful in this case. And remember to test your program really, really step by step. Yep.
Is this due next Tuesday?
It's due next Tuesday. You guys want to postpone that to next Thursday? So then you guys can procrastinate for another 2 days? That's usually what happens. It doesn't really help anything. I'll go ahead and give you guys the 2 extra days.
Well, next it's focusing on the task.
This homework assignment will kind of help with the test too. I'm going to give you like 2 more days. There we go. All right, but don't procrastinate. That's what I keep telling my 6th grader.
Tell me how to do like a save as.